Okay, well, hi everyone. Thank you for inviting me to talk here. So Tom did a great job introducing me on my research topic, which is assessing the feasibility of large-scale hydrogen storage in salt caverns on the UK continental shelf using 3D seismic data. I'm a first-year PhD student within Earth, Ocean, and Planetary Science, so all this research is quite early at the minute. But I'm going to walk you through what I've done so far and my early findings towards the end. So let's begin. I'm just going to move, the Zoom things over. There we go. So current electrical energy demand in the UK is forecast to be between 500 and 630 terawatt hours in 2050. The UK aims to be carbon neutral by this time, but in order to meet this greener goal, better and energy alternatives are going to be needed. Hydrogen is a vital resource in this battle for net zero. All of the 2050 net zero cases calculated by the UK's national grid require at least 150 terawatt hours of hydrogen for true net zero. However, at present day, only 1 terawatt hour of hydrogen is currently produced. Salt caverns provide the opportunity to store large amounts of hydrogen in the subsurface safely, also having a low impact on the surrounding environment. To date, there's only one site within Europe that stores hydrogen within the subsurface, and that's in Teesside. It's stored there for petrochemical purposes in salt caverns. We can see it perfectly on this map. I'm just going to get my pointer up on screen for later. And there are also salt cavern sites in Cheshire for storing natural gas, and there are lots in Germany. However, to date, no salt caverns have been built offshore. Just to add about hydrogen though, it's seen major investment in the last 2 to 3 years, with BP having announced a major blue hydrogen plant in Teesside with over a £1 billion investment, and Equinor's H21 project in Leeds and HyNet Northwest project is really a sign that the hydrogen economy is growing and going to play a big part in the decarbonisation of the energy network in the future. So where's my work concentrating? My work's currently concentrating in the southern North Sea. It's a fantastic area, and we chose this area of research for several reasons. The geology of the southern North Sea is very, very well understood, thanks to decades of hydrocarbon research. I think last time I checked, in the North Sea, there are over 7,800 wells have been drilled. So there's probably just about over 3,000 within the southern North Sea. This gives us an immense amount of data, which the majority is publicly available to us through government portals. Also, in the southern North Sea, there are vast amounts of the Zechstein supergroup evaporites. The Zechstein is a Permian-aged salt unit that I'll talk about a bit more on the salt slide, but that's our target for putting salt caverns into. It stretches all the way from the east coast of England to Poland and can be kilometers thick in areas, so it's a fantastic geological unit for salt caverns. Also, the infrastructure within the southern North Sea is fantastic. The southern North Sea acts as an energy hub to the UK currently, with a lot of gas being produced. However, year after year, there are more and more wind farms being produced. So on this map here, we can see the current planning, consented and operational wind farms from the southern North Sea. So the idea of co-location of storage and production of energy, possibly hydrogen, is a fantastic idea, as it allows infrastructure and economical advantages, with possibly a whole hydrogen hub at some point being developed offshore with production, storage and transportation. Because old gas pipelines can be converted to use to transport hydrogen. So for those of you who aren't geologists, who don't spend their lives looking at rocks like I do, here's just a quick update on where exactly the Zechstein is. So Zechstein is down here. It's a Permian-aged supergroup of evaporites. These formed back in the Permian era, where large oceans filled a basin, the water evaporated and left the salt behind. So very much the same as your table salt. That's what I'm dealing with in subsurface. And here we've got a map of where the Permian actually extends. Here we can see the east coast of England all the way through to Poland. And here's my research area. So as you can see, it's a vast amount of salt in the subsurface, perfect for us to put salt caverns into. Now, I've talked about salt caverns quite a lot. What exactly are they? Well, as they sound, it's an empty volume within a unit of salt. These can be formed via mining into them and putting hot pressurized water into it and dissolving the salt and removing the brine. This is usually done for the cavern space itself, or for the valuable minerals is found within the salt. And here on the diagram on the right, we can see several examples of salt caverns from around the world. So these can be quite big volume-wise. these are all onshore, so the volumes tend to be quite small, but offshore would be aiming at volumes within a singular cavern of sort of 500,000 to 750,000 new cubic meters of space. And you tend to have these caverns in clusters. So I already mentioned the caverns in Teesside. There are 3 there, quite small ones. These store hydrogen for industrial usage. But in Cheshire, there are 20 onshore caverns as well for natural gas storage. So that comes back to cluster, and they store quite a large amount of energy, but relatively speaking, they take up quite a large amount of space onshore. However, offshore, the amount of space we could use is much, much more. So we could get hundreds of caverns possibly, which might get us up to that terawatt hours of storage needed. The important geological parameters to keep in mind for salt cavern storage is that salt needs a maximum depth of 2,000 meters. So all caverns need to be in place above that 2,000 meter mark. The minimum thickness of the salt, it needs to be at least 200 meters thick, and the small number of interbeds of non-porous insoluble lithologies. So you want all that nice pure salt that's dissolved. So how do we locate where to store these caverns? Well, we use 3D seismic data. 3D seismic data is a staple of the oil and gas industry. It allows us to see the subsurface in incredible detail. So here I've got a small sliver of 3D data. So we've got a 3D seismic cube, which is a continuous amount of data, which lets us see the subsurface in just fantastic detail. This technology still amazes me to this day. So here we can see sort of a 100-kilometer section through our area of the Southern North Sea here. And as a geologist, I look at this data and I interpret what I think the boundaries between the different lithological or lithology groups are. So here we can see a little quite fancy interpretation I made. The ones I work with aren't this fancy, but this is nice to present with. So we can see here that this grayish bluish is the salt within the Southern North Sea, and we can see this is very much an overlay for the seismic data above it. So we can see this triangular wedge here correlates with this triangular wedge up here. So that's very much a salt, and that's the unit we want to look at. So we've got this data, but this is a 2D slice, and we want it in 3D and a continuous area throughout the entire Southern North Sea, which we're able to do with some very fun geological software. So this is very much a work in progress so far. Now, I mentioned before we want to know the depth to the salt and the thickness of the salt. Those are the 2 most important parameters that we want to know. Unfortunately, we can calculate this by taking our seismic data and mapping the top of the salt, which is what we've got left on the left here. We've got a map to the depth of the top salt. So the way seismic data works, it's measured in time, not depth. So these figures do need depth converting at some point, but that will come later within this PhD research area. And what we can see from this so far is that we've got a big dome of salt here. We've got a wall of salt going here. Sorry, I should add for the non-geologists that salt is mobile in the subsurface. It's got a density of about 2.2 grams a centimeter cubed, which is a lot less than normal 2.7-ish for regular rocks, which means that the salt is mobile and it can move and form really quite complicated structures in the subsurface. And this mobility allows it to move upwards towards the surface, helping us reach that goal of less than 2,000 meters, but also being incredibly thick. So we've matched the top zechstein, which gives us the depth to it, so we can see if it's above that 2,000 meter mark. We've also mapped the base of it, and we can combine these measurements to give us a thickness map of the zechstein. So on the right here is a thickness map. So we can see that that dome that I pointed to, the pointer just here, is quite thick. It's over 600 milliseconds, which is probably about 700-800 meters thick, which is perfect. And we can see that it's shallow as well. So that looks like a perfect target for hydrogen storage. And so our plan is to go and take this data and go on a zone-by-zone basis and find perfect sites. That might be very good, but unfortunately salt is not one homogeneous lump of sodium chloride. It's quite complicated. The internal heterogeneities can vary greatly, so we need to be able to account for this. And how do we account for this? Well, I mentioned earlier the amount of wells that have been drilled in the Southern North Sea. Here we've got 2 examples of 2 different wells. One's from bedded salt and one's from structured salt. So in the bedded salt, we can see that it starts at 1,100 meters and goes all the way down to 1,800 meters. Again, it's meeting that perfect point of less than 2,000 meters, and it's 200 meters thick. We need to take note of the lithology as well, so you get some carbonates within the zechstein. So we want to look for those units which are purely salt, purely halite, which the top Z2 salt seems to be within this area, which is fantastic. And also within structured salt, so I mentioned earlier, salt's mobile. This preferentially lets the more mobile units, being the halite, go into these areas and gives us very, very deep areas of pure salt, which is fantastic salt cavern storage. So as we can see here, it's about 400 meters deep from the surface, but over 2,000 meters thick, which is absolutely fantastic, exactly what we want. There are also some other complexities with salt, in that it's not all deposited the same. You'll get mini interbeds of less soluble material. And when you're dissolving the salt for the cavern, you need to be able to account for this. So we've come up with a new log, which is the lithosolubility log. So from this, we take the petrophysical readings of the well and the well reports, and we combine them into categorize how soluble we think that material is. And we keep halite as the base solubility of 100%. You get other lithologies such as carnallite, which is more soluble, and carbonates and hydrite, which are less soluble. And then we apply a rating to this. This is important to keep track of, because when you're dissolving a cavern, if say all the cavern's 90% soluble halite we've judged, you'll get 10% of insolubles left at the bottom of the cavern, which takes up very valuable cavern space for volumetrics and can lead to instability. So we've got the big scale, we've mapped the entire stuff, and obviously we've got the small scale. We need to be able to combine these to see what's happening on a site-by-site basis. Fortunately, what we can do is we can take a small section. So here you can see on the right, this is just the cross-section of this area of 3D seismic survey. And we can take the well data from nearby and we can overlay these on each other. So this data comes from the bedded salt seen previously. And we can split the salt into the units within the seismic data. Normally in oil and gas, you're not able to do this, but we've got very good data. So this allows us to split the separate Z units apart from each other. And as seen on the previous slide quickly, we've got the top Z2, which has got lots of very pure halite in, which is a fantastic target. And then we can see this as well on the seismic data, which is fantastic. So we can see where it's suitable, how deep it is, so we know the targets to drill in and start to plan these caverns in a 3D environment. So it's fantastic being able to differentiate, because this allows us to see the risks, the uncertainties, because you don't want to go through a carbonate layer, because carbonates are porous and permeable and may allow for escape of hydrogen, which is something you want to avoid at all costs. So that's bedded salt. This area of bedded salt, I think, is it's a large area. I don't have the calculation on the top of my head, but I think it's hundreds of kilometers squared, which means you could fit quite a large amount of caverns in. Again, unfortunately, I'm not at the point of volumetric calculation or cavern placement in my research, but that should come sooner down the line. So that's a piece of bedded salt. What does structured salt look like? It's much the same. So as you can see here, there's very much a well that's been overlaid on this bit of seismic data. This is about 2,000 meters, as I mentioned earlier. And we can see here that this area with not many reflectors in it is pure halite. However, we don't get as good an image as we do with the bedded salt. So there's a lot more uncertainties of other lithological interbeds which might solve problems. Which might cause problems rather. So we can interpret this, but not as well as in finer details as bedded salt, even though this is possibly a much better target due to its much shallower depth and the much, much thicker amount of halite. We can't see those little intricacies within the seismic data, unfortunately. So this unknown internal lithostratigraphic structure may lead to some problems. However, we have a possible way of dealing with this, in that we can use analogs. So these salt structures are often mined in areas like Germany for their valuable salt evaporite resources in them. And then from those mine passages away, they've been mapped. And this gives us a fantastic view of the internal geometry and heterogeneity within these salt structures. So here we can see here that the Z2 halite, which was the lovely thick piece perfect earlier, has preferentially gone to the top. That's likely because of some less dense evaporites in there, causing the structure and the deformation, which plays very well for possible hydrogen storage options, because it means more suitable salts in the top. So I need to do more research into this. It's slightly early days, but it's looking very promising so far. And it's just a very cool diagram as well, so I've got to include that. So that is my early findings so far. We found areas which are suitable for hydrogen storage. We have yet to apply zones to this. This will be happening the next couple of months, hopefully. A lot of salt structures do seem very promising, and the bedded salt up here, which was this area of seismic, also looks very promising, which hopefully means that, you know, the 2050 net zero aims for the government will be able to possibly help this hydrogen storage, because it was a crazy amount of hydrogen, at least 150 terawatt hours which is a substantial amount. However, today, we're making less than 1 terawatt hour. But as technology increases, the cost of green hydrogen will get cheaper. I believe that's forecast to be cheaper than blue hydrogen by 2030, which would be fantastic, which can mean we can start really pushing forward this hydrogen economy and start really to decarbonize a lot of stuff and decarbonize the heating, the network, and everything. So yeah, that's it. Thank you all very much for listening to me waffle on about salt cavern storage for the last 15 minutes. I just want to thank the GeoNet Zero CDD for funding my PhD research, the Oil and Gas Association for providing the seismic data, and Schlumberger for access to their Petrol 2020 software. Here are some references from the talk. Please, any questions, I'm happy to answer them. Thank you.
Thank you very much, Hector. That was really, really interesting. As you said, are there any questions? I have a couple to start off.
Yeah, go for it.
First of all, I'm a geoscientist, but I don't know that much about salt. Is there a reason why they have to be less than 2,000 meters deep?
Yeah, it comes down to the pressures within the caverns. So if you've got a cavern within your salt, and I think they're looking to be about I should really know off the top of my head, a couple hundred meters deep. About 50 meters wide, a couple hundred meters deep. There's a lot of risk of caverns collapsing in on themselves at deeper, just because the overburden pressures associated with having large voids in salt can lead to these issues. And also, it comes down to the pressure operating within the hydrogen inside. So the hydrogen inside these caverns needs to be about 80% of the overburden pressure. And beyond 2,000 meters, this pressure inside can then start to fracture the salt, which can lead to pathways for leakage. So it's mainly for a geosafety aspect. There are some projects that have proposed putting caverns in salt as deep as 2,500 meters. But it's a rule of thumb to keep it above 2,000 meters at this point for safety and operating aspects.
Brilliant. I was also going to ask if you thought, because obviously this is seasonal storage, I assume, of hydrogen.
Yes, so it could be both, to be honest. I think the way not many people have incorporated this into their models purely because it doesn't exist that much at the minute, but it very much could be used. You've got your offshore wind farms generating electricity. If not much is being used in the summer or in the evenings, you can use that excess energy to generate hydrogen and then store it in these salt caverns. And then times when we come to use it, it can be extracted. So I think it very much depends on a project or the logistics behind it. But the joys about salt cavern is it's got very, very quick. You can get the gas out there very quickly. Unlike possibly storage in an abandoned oil and gas reservoir, the withdrawal rate is much, much slower than hydrogen caverns. So I think a hydrogen cavern, it's in days scale rather than weeks for porous media. So I think, yes, it could very much be it's seasonal, or you can, if the footy's on, for example, and everyone's going to make a cup of tea and you need a lot of energy quickly during the summer for some reason. Yeah, no, exactly. It's just a fantastic storage medium and a good energy storage medium as well for exactly that issue. Yeah.